Well, welcome to AP Precalculus Live. This is Thursday night. My name is Curtis Brown, and I am joined by Steve Kokoska, Tom Dick, and Vicky Carter. Super excited to have you guys here again for another season of these videos. This year, tonight, we're going to be looking at the pre-cal year one insights. So thinking back on really the exam and things that we can learn from both what students did during the exam and maybe what was going on for them. That's the kind of stuff we're going to be checking out. So really excited to be doing that with you guys tonight. And so Steve, Vicky, Tom, I don't remember who's starting. Go ahead
I'm
and
going
hit
to
play.
try.
All right.
All right, here we go. How about that, Curtis? Can you see that screen?
I can see that screen.
Beautiful. All right. Well, thank you very much, Curtis, for arranging this again this academic year. And Vicky and Tom, it's wonderful to be working with you again. So tonight, what we're going to try, Curtis, is we're going to take a look at a couple of the free response questions from the first pre-calculus exam. And what we're going to try to do is we're going to take a look at a free response question. I'm going to try to solve that in a way that I think about it, that maybe students would think about it. I'm going to look at the scoring guidelines very quickly. Then I may hand it over to Tom, if appropriate, to do a little bit of technology. Then we'll come back and we'll try to decipher the scoring notes. Because although these are published, these bulleted items are sometimes difficult to interpret, and we'll do our best to interpret these. Now, full disclosure, as Vicky says, the three of us, we were not at the AP pre-calculus reading, but we're using our experience from participating in the calculus reading and from writing questions for the pre-calculus exam. So being involved in that process, I think, has helped us quite a bit. So Curtis, this process, this kind of a presentation usually lends itself to a lot of questions from the participants. So I'm going to ask you to monitor that chat and please ask questions, and Curtis will get them to us as soon as possible. I think if I remember correctly, Curtis, there is a little bit of a lag, but please feel free to interrupt. We're not offended in any way. And
Yes, there is a little bit of a delay.
okay, and then eventually, towards the end of the presentation, we just want to remind everybody about the digital exam, where it's going to be partially or hybrid digital next year. And we wanted to remind everybody about the TI built-in digital calculators and just give you a quick peek at that to make sure that you are aware that that is available and to make sure that you say something to the College Board about this if you are desire to do so. So, okay, let's start out by taking a look at question one. Question one, where a graphing calculator was required. And I just put a little note to myself off to the top right-hand side there. This is worth 6 points. And the way that we grade these papers these days is that we want students to earn points. We don't think about 6 points and students losing points. We look for student work that says, they earn a point for that work. So we don't want to take away anything from the student. We're looking for places where they earn credit. So in this question, we have the graph of a function f, and its domain is minus 3.5 to 3.5. With a little bit of luck, I can write on this screen. That's kind of weird to me. I don't know why they did that. Usually they would choose integer endpoints for the domain. I'm guessing that if they went -4 to +4, there would have been some sort of, not conflict, but possible confusion with one of the answers, but I'm not sure about that. They tell us explicitly that the points -3, 1, 0, 1, and 3, 1 are on the graph of f. So although it certainly looks that way from the graph, they are indeed reinforcing that idea. And then we have this new function g, which is an exponential function given to us. All right, so finally, after all of that, the function h is defined to be a composite function, g circle f of x. And to me, this is kind of nice of the College Board or ETS to do this, College Board, I guess, to actually give us the definition of that composite function. That's a common error, is that if that is not given and students only see this sort of expression, students might be confused about, well, do I evaluate F first or do I evaluate G first? So it's kind of nice that they gave us that. It says first, find the value of h of 3 as a decimal approximation. I'm going to underline a little bit here just for my own benefit. They actually do want that decimal approximation. That might be just a fuzz different from the calculus exam, and I'll show you where in a minute. Or indicate that it's not defined. It might not be defined. And then in 2, find all the values of x for which f of x is equal to 1, or indicate that there aren't any such values. So I think in AP Precalculus lingo, we are looking for all the inputs that lead us to that output of 1. So, okay, how would I solve this one? I'm going to try to arrow up just a little bit if I can, Curtis. Let's see if this is working. How about that? So what I would do here is I would go right to the definition. I want h of 3, which is g of f of 3. How do I evaluate that inner function? Well, my only choice is to go to the graph and look at the y value that corresponds to the x value of 3. And I can actually get that in 2 ways. I can look at the graph. If I didn't read the problem carefully enough, I can see that that value is 1. But they've also given me here in this problem that this 0.31 is on the graph. So I know that f of 3 is equal to 1. So now how do I evaluate g, that outer function, at 1? Well, I've got an expression, an analytic or algebraic expression for g. So I plug 1 in. There's the little 1. It's kind of small, but there it is. And I'm left with this, but I can't stop there in this problem. They're actually asking us for this decimal approximation. Now, those of us who are familiar with AP Calculus know that a final numerical answer can be left like that. But in this case, on this exam, they're looking for a decimal approximation. And so they want this answer right here. And I'm going to scribble a little bit more too, Curtis, off to the side. The full answer, or with more decimal places here, I believe, is 2.0412 if you do that multiplication. But as in AP Calculus, all we need are 3 digits to the right of the decimal, rounded or truncated. So rounded or truncated, this is still 2.041, and that's what we're looking for. If the 2 is provided, that's fine. We're actually going to ignore that 2, and I'll show you that more explicitly in a minute or two. But we do need that decimal approximation. Great. How do I solve 2? Well, find all the values for which f of x is equal to 1. Well, I can get this in a couple of ways here, but I have to find all the values. So I'm sorry, Curtis, I'm going to try this, see if this works. I'm going to actually arrow it down a little bit so I can see that graph. You know, I know right away that there are 3 values that lead to 1. I know there's a -3, a 0, and an x equal 3 as input values lead to output values of 1. But how do I know that's all of them? Well, I might come up to the graph here, and if you can see that, I might draw a horizontal line here at y equal 1. And I can see that that line intersects the graph at no other places, only at those 3. -3, x equals 0, and x equals 3. So that's all the values. That's all I do in my solution. And I hope that that would give me those 2 points. So what were the scoring guidelines here? How were the points awarded? Well, the first point was awarded for that value of 2.041. And this is interesting. The second point was awarded for the values -3, 0, and 3. We need to see all 3 of those. Are there instances in which partial credit can be earned? Yes, kind of some odd ways here, but yes, that's possible. But those are how the 2 points were earned. Tom, I'm going to stop there for a second. Would you like to do any technology associated with this?
Sure, Steve, but before you leave
Yes.
your screen, if you could scroll up a bit to your graph, there was
Okay.
a comment I was going to make.
Okay.
And it actually goes to your initial musing about the domain of this being -3.5 to 3.5.
Yes.
And I've got a conjecture on that, and it goes a couple of ways.
Okay.
The wording on part 2 of part A here is find all the values of X. And we really know we have all the values of X because we really do have a complete graph of
True.
the complete graph of F fits on that screen. And I think they probably, this is a conjecture on they made those endpoints be at fractional values of X to really make it very prominent that there are endpoints to the graph. See, so it's not on the grid. So there's like no question, you've got the whole whole shebang here. So that's
sure.
and it makes it totally unambiguous. It's all values. You don't have to worry. Well, what's the graph doing off the grid? I can see. Well,
Sure.
no, we've got it all. It's all right here in this bounded interval. So anyhow, okay. So let's see.
There you go.
All right. Let me attempt to share my screen, and let me know if I've been successful.
There you go. Looks good, Tom.
Okay, great. So just looking at this problem Steve's been reviewing here, it's a chance this was on the calculator open part of the exam, and certainly the way that function G was presented, you could guess you were going to need a calculator to do some calculations. When you have a problem like that, I think a best practice using the calculator is to get that a function you're going to be working with repeatedly, get that thing stored away so you can have it available and do different things with it. So I've gone to the y equals menu here, and I'm going to enter that function we've been working with. Now, this is the function that actually has a formula to it. So that's that 2.916 times 0.7 raised to the x power. So there's our exponential function. Now, this is the function g. And the first question, it was a composition, but it's essentially evaluating g at a particular value. Okay. So let's go ahead and take a quick look at the graph of this function. I'm going to use my zoom menu here and actually do a zoom decimal. So that's number 4. And we should see, okay. And I could do kind of a reality check here right off the bat and say, well, does this graph make sense to me? Well, we've got an exponential. Let me just jump back to y equals again. And let's see, 0.7. Oh, that's a number less than 1. So that exponential curve should be like decreasing as we go from left to right. A couple of values that should jump out at me when x is 0. I should get 2.916 times 1, right? 0.7 to the 0 power. So it should have a y-intercept just under 3. So when I go back to the graph, it looks really good. Okay, so that's just a visual reality check there. And then we could trace. And in fact, that would be a way to get that first calculation value. We could actually trace over to x equals 1. Now,
Tom, that's working because of the window that you actually used. So if they had done something like this, what they consider the standard window, they might not trace and actually hit on the value at 1.
Yeah, so let's go ahead and do that. Let's do a zoom.
Oh, okay.
Yeah, here's a zoom standard, and now if I trace, oh, wow, it's a really weird increment. You can see that the x is it's going up by 0.15 and some change. Yeah, it's a weird value. The nice thing to know is that whatever your window is, if you're on trace and you want to go to a very specific value, just type it in. So I'm going to type in 1. And now it's going to jump to exactly x equal 1. Regardless of what my window is, even if I would miss it if I was tracing. So let's try that. Bingo. There's that 2.0412. that we were talking about. So great.
So these are some really good things, tools or whatever that students need to have when they're using their calculator to know that they can do something like that, and not just depend on those trace steps that they have in whatever window they happen to have used.
Yeah, that jump trace is really nice. Another quick thing, Tom, if
Yeah.
you wanted to get back to that window you had just a moment ago,
So the
press
zoom
the zoom, go to memory,
Okay.
and do zoom previous.
Zoom previous. Okay. So if you wanted to
If you messed up your window or changed the window,
kind of
you can
like
do
an
zoom
undo when you're
previous.
zooming.
Yep.
Yeah.
Mhm. Exactly.
There you go. And let me do the trace again, and I'll take a shortcut by just typing in 1 immediately. So there we go. And you did want to show one other thing here is with that our function g of x stored in y1, if I was to quit, just go to my calculator screen, I could pull up y1 by going to y variables, there's function, there's y1, and evaluate it at any number I want to. In this case, if we wanted to evaluate at 1, we'll just type in y1 of 1. And there we see that value. Yeah. So that's another. And the thing is that function g now is stored away in y1 safely. We don't have to be kind of retyping it in every time that we're using it. So it really saves some time and makes your work a little bit more precise.
And I highly recommend. So we know that on the task model for free response 1, that there will be one function given analytically, which is what that g of x is. I would immediately type it into my calculator, knowing that it's a calculator active question, so that whatever I needed to do, whether it's what Tom just did or using the graphing screen, you can utilize that function over and over and over, and you don't have to retype it.
Vicki, may I ask, would you recommend that students, when they take the exam, set their calculator to fix 3 so that they always get only 3 digits to the right?
I mean, that is a good thing to do. I don't necessarily do that myself. I'd kind of like to see a few more digits. For instance, I like seeing the 4 digits here for some reason. But students do need to know that the calculator is going to round these values. So don't, I don't know how to say this, round, like
Right. No intermediate rounding, right?
Right.
And I think that's my one resistance to the concept of having it set on fixed 3, because it could tempt a student to, well, I always only see 3 decimal places, so they might not think to store a value or
Yes.
use that value in a later case at its full precision. Hey, Tom, we did get a request in the chat to repeat that Zoom jump, the jump trace option. So I don't know if you want to just pop back over to the graph screen real quick and do trace and then jump to a value.
Okay. So I'll just
just to reiterate the process of being able to trace to any value. You might trace to the value at 2, just so we can
just try something different.
So I could be just tracing by whatever increment my window happens to be. A zoom decimal, you have like a super nice increment. It's 0.1 each time. So you're going to hit nice integer values. But if I want to go out all the way out to say, let's see, 3.5, let's say, rather than trace 0.1 at a time, I'll just type in 3.5 and hit enter, and it should jump immediately to that value. So something, it's easy to jump from value to value to value if you wanted to. Yes.
So Tom, can you also, of course, jump to a value that would not be hit by trace? For example, in this window, could you type in 3.123?
Oh, yeah. Well, yeah. And that's what happened with that Zoom standard window is we wouldn't actually hit 1 with the trace, but 3.123, enter it, boom, there it is.
There you go.
Even though that's not a specific trace value that we normally.
Yep.
You might wonder, and I'm just going to see what happens. What if we try to jump to a value off the screen?
Okay.
Just give it a shot, see what happens. I'll type in 10. Okay. So this shows you that, if the value you jump to needs to be inside your window at the time.
Gotcha.
So show, in case folks were wondering, could you jump out to 10,000 or whatever? Okay. However, you're not limited to that if you're on the calculator screen. Right? So I could have done, I just went up and echoed my Y1 of 1. I'm just going to make that Y1 of 10. This doesn't care what the window is at all. I can type in any value I want and evaluate what I want. So all the flexibility in the world if you're evaluating the function on the calculator screen. All right. That's about all I had for this one.
Okay.
Stop the share and turn it back over to you, Steve, unless.
Okay, great. Thank you.
Okay, there we go.
Beautiful. There we go. So in question 1, in free response question 1, there were some general notes about scoring here, which mainly, I think, dealt with decimal approximations. So I'm going to try to summarize what's going on here in these 3 bullet points. First of all, if there are trailing zeros, you don't need them. And sometimes students make what's called the decimal presentation error, but we don't want to, we want students to be able to earn some points, even if they make that error more than one time in a problem. So the word that we used to use for this is inoculated. So if a person makes a decimal approximation error, and what that means is, well, we're looking for 3 digits to the right of the decimal. Maybe they only give us 1 or 2. But those 2 digits that they give me are correct, but they've made an error. They didn't give me the 3rd. So that's a decimal presentation error. So they will not earn that point. But if they make another decimal approximation error later on in this one problem, they are still eligible to earn that point. So I don't like to say it this way, but we will not dock them twice or 3 times, or more than once for a decimal approximation error. Okay, so the scoring notes. Let's see if we can decipher some of these. A couple of interesting ones here. I'm going to arrow down a little bit if I can. Okay, how about that working? So the first point is earned for the correct decimal approximation of 2.041. I added in a possible response from a student, 2.0412. Well, that's the full answer. I think it terminates there, but I'm going to put a little line there, a little box there, bracket. We don't read past that 3rd digit. So if a student had responded that, well, H of 3 is equal to 2.0419, they're still going to earn the point. We're not going to read that 4th digit and beyond. Now, the second point in the scoring of this exam did not require any supporting work. So that means if the student just wrote down -3, 0, and 3, they would earn the point. But here's a couple of possibilities here. So a student might say, well, I need to solve this expression, and I see it happens at the input values of -3 and 3. Well, that's not all the values. So if we're scoring just part 2 here, in my way of writing things, I don't know what happened in part 1, but they would not earn the point in part 2. Now, yes, you're right. There's still some partial credit things to think about, but I'm just looking at these 2 parts separately. Another way that a student might respond here is they might actually respond with the coordinate pairs, -3, 1, 0, 1, and 3, 1. That's actually given in the statement of the problem. And as long as those y coordinates are correct, they would earn the point for those 3 ordered pairs. Now, there was this kind of an odd 2-column approach here for partial credit. This is something that I have not seen before, and I don't know if it's going to make its way into calculus or not. But the reason for this is, I'm pretty sure, is that we want to award credit for good pre-calculus work. And so this was a way to give students some credit. We didn't have everything completely right. So I'm going to write down a couple of things and see if I got this correct, okay? So I'm going to write down, let's see, 2.916 times 0.07 over here. And I'm going to write down an x equal minus 3 over there. And then below this, I'm going to write down a 2.04. And over here, I'm going to write down x equal minus 3 and 3. All right. So here, the student has expressed the answer, but not as a final decimal. So they didn't go far enough. And they reported, well, only one correct value. So they've done some things right, but they didn't quite get to the final answer. So if I'm reading this first column and second column correctly, I think they'd get 1 point for that. And I think the way that it was awarded was a 0-1. Now, a student might also report 2.04. Well, okay.
Hey, Steve,
Yes, sir.
real quick on that, and you may or may not have the information, but if a student just gave the list, like in bracket form, -303 without an X, is that
So like this?
Yeah, so just
Okay. I think if I saw that in part 2, I would give that answer. I would give that credit. I'd give that the point for sure.
Yeah. They didn't need to say X equals. Okay.
No, I don't think so. I think that's okay, Curtis. A student might also respond down here 2.04. Well, let's see. That's the correct value, but it's got a decimal presentation error. I don't have the 3 digits. And over here, they gave me 2 correct values. Well, let's see. There's no other values included, so if they gave me this and this, they'd earn partial credit. Now, the way that I read this is it's one thing from the first column and one thing from the second. So actually, if they did this decimal presentation error and reported this, they'd also get 1 point. And if they made this error with this, they'd also get 1 point. So I suspect as the readers were looking at this, they saw lots of this and it became ingrained and easy to see. It took me a little while to think about this and understand what's going on.
So Steve,
Oh, I'm sorry.
No, I was just going to say, apparently the y-intercept was the one that a lot of students happened to leave off, and we're a little perplexed by that. But anyway, it's the one that seemed to be omitted in many cases. Yeah.
So they left off the x equals 0.
0, yeah.
Interesting. I wonder why.
Or they transposed and said it was x equals 1 or something like that.
Huh.
I could see x equals 0 being ignored because they just skip over value. You know, it's x0, so it doesn't really count.
It doesn't count.
Doesn't count.
Yeah. I mean, for real, it sounds silly, but I think it's a very valid potential ignore because it's x equals 0. I think that's an easy one to skip over.
Okay. All right, well, let's see if we can look at part B here. So in B, we have to find all the values of x as decimal approximations for which g of x is equal to 2. So we're doing something similar to what we did a minute ago, but this time with the function g. And we have to find all values of x for which that's true. Or, again, indicate that there aren't any such values. Okay, so let's see. In 2, we have to determine the end behavior of g as x increases without bound. And we want to use mathematical notation to express this end behavior. We want to use limit notation. So let me show you how I might solve these and show you what the scoring guidelines look like, and we'll get to some technology. I'm going to show you a couple of screens, and we'll get to Tom in a second. So, all right, I have to solve this problem right here. I have to solve g of x is equal to 2. I have to find all the x values that lead me to a 2. So here's the expression for g of x. So now I have to solve this expression. Well, I'm going to do a little bit of this by hand and then eventually get to the calculator. So let's see, in order to solve that, I think what I do is I bring the 2.916 to the other side, and I've got a decimal here. I actually did that division. I'm going to stop for just a second and remind you that if you do an intermediate calculation like this, you certainly ought to store that to the greatest degree of accuracy allowed by the technology. And I think Tom will show you a little bit of this. So now I'm going to take the natural log of both sides. I'm going to employ a property of log so that x will come out in front. Then I'll have to divide both sides by that natural log of 0.7. And eventually, after all of that, I believe the answer is x equal to 1.057. Now, to back that up a little bit, I'm going to go to technology. I'm actually going to solve this, Curtis, if it's okay, in two different ways. I'm going to look at a graph screen first over here on the left-hand side. And what I did is I graphed the function g as Tom did, but in a viewing window, 0 to 2 along the x-axis and 0 to 4 along the y-axis. Now, this screen illustration is annotated. I've actually added those window parameters, those window boundaries myself onto this screen illustration. That's not part of the TI-84. You can't do that in the machine, but I've done that with a little bit of using LaTeX here. Now, I've also added some annotation to make this a little bit easier for me to see. Well, that's the graph of G, and that green line, if you can see the colors, is a horizontal line y equal 2. And what I need to do is to find out, well, where do those two graphs intersect? Well, there is a built-in function in the TI-84 to find out where two curves intersect. So I use that function, and you can see the x equal 1.057 down below. You can see sort of my, not pointer, but my little x there is at the point of intersection. So that's one way to do it. I think a lot of students, this is just a guess, like to do it that way sort of visually, and that's fine. That gives you the correct value of x. You have to make sure that you aren't missing any values of x here. So you may have to adjust the window parameters 2 or 3 times to make sure that you've got all the values of x. And another way to do this with a TI-84 is with the numerical solve feature. I happen to like this one. So you can actually enter in 2 expressions and set them equal, and set a bound and a guess, and then hit the solve key. And the calculator will actually, with the numerical algorithm in the background, return this value of x that solves this equation. G of x is equal to 2. And son of a gun, fortunately, I do have the 1.057 in there also. So I've got my answer to part 1, part I here. X is equal to 1.057. What happens as x increases without bound? Well, let's see. I'm thinking out loud a little bit and writing. As x increases without bound, I'm looking at my function g right here. As x increases without bound, I know that that 0.7, since that 0.7 is less than 1, as x gets bigger and bigger, I know that that 0.7 raised to the x gets smaller and smaller and goes to 0. The 2.916 is constant, so that constant times a value that's getting smaller and smaller and smaller is going to 0. How do I express that using limit notation? Well, that's right here. That's the limit as x goes to infinity of g of x is equal to 0. Okay, what do the scoring guidelines look like here? Well, there was 1 point for that value. We're looking for that input value that leads to an output of 2 using the function g. So we're looking for that 1.057. And there's 1 point for the end behavior with the limit notation. So we're really looking for that limit as x goes to infinity of g of x is equal to 0. It's a little unclear to me as if I were just reading these scoring guidelines, if I hadn't participated in the reading, if I hadn't participated in writing some of these questions. Do I really need to see some wording? Do I really need to see as x increases without bound, g is getting close to 0. I don't believe so. I believe that limit notation is sufficient to earn that point. You can write some other things there so long as it's correct, but I really need to see that limit notation.
So, Steve, it's also important that they use correct limit notation. So students definitely need practice with that in the classroom, that all the, I guess we can call it components of a limit expression, are shown when they write that on their exam.
Yes, and we'll look at some of those in a minute, Vicky. That's an excellent point. Excellent point. Tom, a little bit of technology?
Sure, Steve. Sounds good.
Okay. There you are, sir.
All right. There we go. Share my screen. Hopefully we got that back up again. Great. And at the risk of being a little bit redundant, Steve, I thought I would just kind of run through how you got those screens that you
Yeah,
got.
please, Tom. Yeah,
So
I think it's a good idea.
See how to do that.
Yeah.
So I'm going to go back to the y equals. And again, we've got, our function g's in there already. You had also graphed the horizontal line, y equals 2.
Correct.
You can do that just by entering 2 for our y2 equation. And then let me just go ahead now, do a zoom. I'll do a zoom decimal again. And this should bring up both of those graphs. Good enough. And if I trace, now it's tracing the blue graph is my g of x function. If I hit the up or down arrow, it'll toggle over to the other. Now, the other function's not too exciting because its value is always 2. But if I hit the up arrow again, now if I trace and just move over to where it, close to where it's crossing, let's see, when I get to 1, well, that's familiar. That's that 2.0412. I go one more pixel over. Oh, now I'm under 2. So I was a little bit over 2. I'm a bit up 2. Looking at the graphs, I'm guessing, well, I think that solution is probably between 1 and 1.1. Okay. To get it more exactly, let's go to the calc. That's going to be the second of trace. There's that calc label there. And I have some choices of things I can calculate right on the graph screen. So I can calculate a function value, a 0. Let's see, number 5 looks like a good one, intersect. Okay, so let me, you can either type in 5 or scroll down there and hit enter. And it says, okay, well, what's the 2 curves you're interested in? Well, we've only got 2, so our choice is pretty clear. First curve is the blue one. That's our g of x. So I'll hit enter. It says, how about the second curve? You want it to be that y2 equals 2. Sure enough. And now it's asking me for a guess that's close to that value. Well, I'm pretty darn close already, I think. So I'm going to just go ahead and hit enter. And it should, boom, there it is. There's that 1.057168. So we've got a good value there. And want to show that that value actually is, if I'm going to quit from the graph screen, if I was to actually just call up x and enter, that's the current value of x. Okay, so I could store that away. For example, if I was going to use that for a future purpose, like I needed that value for another part of the question, I could do store. Store is right above the on key. So it's going to take that answer I just got. I could store it, say, in A. And now if I do some other things with my graph screen and I change the value of x because I'm tracing over to other values or whatever, I've got this safely stored away in it. The other thing I want to show was how to use that equation solver that you were.
Okay.
Corner, you can see that there's it says solve in green above the enter key. That's not what we want. Okay, the equation solver is actually under the math menu. So if you go to the math menu, and under that math submenu, it doesn't show here, but if we just scroll down, keep going. We hit some extra stuff here, some additional stuff beyond the stuff that showed on the original screen. And I get down here where it says numeric solver. That's the one I want. So let me repeat that. The math menu, go down till you hit numeric solver, hit enter, and then it's going to ask you to put in the two sides of the equation. Now let me go ahead and clear this out. I could either type that in, but you saw what I already had in there was Y1. So I had gone to the variables menu and picked up my function Y1. And I could do Y2, or in this case, because it's just 2, I went ahead and typed in 2. Okay,
So Tom, it's not necessary up in equation 1 to put y1 of x?
No, not at all. Yeah, we can be, because y1 is that expression actually. So
gotcha. Okay.
So if I now let's see, there's a okay. If I'm satisfied with my equation, the OK key, it looks like that's lining up with the fifth key along the top. So I'll hit the graph key, and boom, there it is. There's that solution, and it's actually done that within the pretty huge set of values there. Yes,
so
go
Tom,
ahead.
two things. So we sometimes call those soft keys. So they're indicated at the bottom of the screen, but you just have to use the related key on the keyboard. So in this case, like he said, it was graph would be the solve key. The other thing is students should, and this goes back to something Steve was talking about, they should understand that that exponential function is either always increasing or always decreasing, so that there is only one point of intersection, and have that knowledge to not worry about a second point of intersection.
Yeah, that's a great point. I just hit solving it. Yeah.
I think that X came up because it was stored there, Tom.
Oh, okay. It was, I see what you're saying. It was thinking that was my guess.
Yeah, I think so.
I really guessed well, huh?
Yeah, sure. That was
you
terrific.
guessed already. Yeah.
How'd you remember all those digits?
The intersection.
That value of X, once you used that in the intersect tool, that value is stored in the variable X.
Yeah.
And that X is common throughout the whole calculator. So that X got drawn in here as the current value of X.
Right.
Gotcha.
If you had moved your cursor around, or if you had...
I'm just entering a different value. I'm going to try solve.
Sure,
again.
try entering a different value. And now if you hit solve...
And it still comes back.
It will still come back to that.
To guess, which was pretty far off, but it was...
Right, right. So it really is about the fact that you pulled that in from the other...
Yes.
The other location.
Guys, I forgot about that. I thought it was just coming up with that on the get-go.
Yeah, that's a really good guess. No, you'll also see that when you change that value, so if you edit that again, notice that the little dot on the left-hand side goes away. So if you clear that out.
Yeah, hit a 2 or something there.
Or hit a 2 or a something else.
I just did a clear.
And then type in 6 or 100 or whatever. It doesn't put that dot there until you hit the solve key.
And this is where on Steve's screen he had shown that he had entered a bounds of 0 to 2.
Right.
Where I can leave these bounds as being just basically the full limit of magnitudes that the calculator can deal with, or I could enter my own bounds here. Right?
Sure.
Yeah.
You think the solution somewhere in between these? Yeah.
So I could go from -10 to 10. Let's say.
So this is a way, of course, if you had a function that had more than one input, and you had some idea by looking at the graph screen about where those values might lie, you can change your bound here and find the 2 on this screen.
Right.
Right?
So now I'm going to try with this guess and that bound. I'll just hit let's see, can I just hit?
Oop, you had that F arrow up, I think.
Oh, okay. So let's see if I lost everything I had, or if I'm just going back to the solver, numeric solver. That looks okay. Ah, interesting. We got 6.6. Not sure why. Put 6 in again.
So that's interesting, Curtis. That did change because that was the last X in that graph screen.
Right.
Yeah, very good, very good.
Right.
Yeah,
So if he had done something else and moved the cursor around on the graph screen, so that's the interesting thing that to just note. You know how a lot of us probably think about or have sort of in our heads that the X and Y coordinates, or sorry, rather, all of the variables start off with a default value of 0. Well, that's true until you start tracing around on the graph screen.
Yeah.
And then you have adjusted the value that's stored in X and Y. So it's worth remembering that X and Y, you can store stuff to them, you can use them, but they are associated with the cursor, the position of the cursor, or the output of this solution. So if you go to the home screen right now, the calculator screen, Tom, and you type in X and hit enter, it's gonna report that value because that's the value that's stored in the value of X.
From the solver.
Right, from the solver.
Right.
So it's just kind of worth being aware of X and Y. They're not great values to store things to, but they are really useful if you've used the trace key or something else and you wanted to use that value somewhere. You know that you have both the X and the Y already saved in X and Y.
Yeah. And one last note, I hope it's not too much in the weeds, but that very last line that we saw in the solver where it said E1 minus E2 equals 0.
Yes.
It's just telling us that it, as far as it could tell, there was no difference at all when it plugs that value in to the two sides of the equation. Sometimes it tries to find a solution and it's not quite able to get the two sides equal. So it'll tell you in that last line how close it got, which may be of interest at some point. Anyways, I think I'll stop share and turn it back over to you, Steve, unless
all right.
comments.
Sounds good. Okay, here we go. So here are the scoring notes, these bulleted items that go along with this part B. So the first point is earned for a correct decimal approximation. Once again, we're looking for that 1.057. And the student can't include any incorrect values. So for example, if a student did some work and said, well, I've got X equal to 1.057, and for whatever reason, they report 2.356. Well, unfortunately, they will not earn the point. Okay, there's only one value here, and that's what we want to see. The second point is a little bit more interesting. It's earned for a correct limit statement. And as Vicky mentioned earlier, they're really looking for 4 parts to this. They're looking for LIM, limit. They're looking for as X goes to infinity, the function G, and darn it, the value 0. So we really want to see those 4 items. Now, one thing that's sort of missing in there, you might think, is an equal sign. But we'll deal with that in a second. So students could earn this point by writing this. I'm sorry I couldn't spread this out a little bit more. The limit as X goes to infinity of G of X is 0. Or they could do this with just G in there. Either one of those, they'll earn the point. Instead of writing an equal sign, they could use a right arrow like this. Now, some of you might cringe at that, and some of you might not give credit for that in your class. But in the context of a high stakes exam under some pressure, we're going to give that to the student. They've conveyed enough here to earn the point. This one's sort of in a gray area maybe for me, but it still earns the point, and that is if there's nothing in between. So if a student writes something like this, the limit as x goes to infinity of g of x, and there's a zero nearby, they're going to earn the point. Even if there's no equal sign in there, even if there's no arrow in there. Okay, I know what Curtis is thinking. How close is nearby? I don't know, Curtis. That's a professional judgment, I think. But if it's on the same line, if it's pretty darn close, be pretty clear. I'm going to scribble a little bit more over here. I might write this again later on, but a student might write something like this: a limit of g of x is equal to 0. That does not earn the point. And the reason is because that x going to infinity, that part of the limit notation is lacking. Now, the responses here may include additional information. The student may say, well, I feel like I've got to report some other stuff. Well, if they report other information, it has to be correct. We have a phrase for this in AP Calculus, and that is saying too much. Sometimes a student may include some extra information that just isn't correct, and then they will not earn this point. Here's one of them. They might say that the limit as x goes to infinity of f of x is equal to 0. Well, that's not true. And so they would not earn the point. I could see this as a common error, though, including here f rather than g. But nevertheless, if they include this additional information, they will not earn the point. And if they write the limit as x goes to infinity of g of x is minus infinity, well, that's certainly not right, and they're not going to earn that point. I don't know if that would be additional information again. They might write something like this: the limit as x goes to minus infinity of g of x is equal to minus infinity. Well, that's not right, and they would not earn the point. Now, in this particular problem here, in the interest of time, there was a first column and a second column sort of thing similar to Part A, where a student could earn some partial credit. But we won't talk about that now in the interest of time. Let's see if we can take a quick look here at Part C. So in C, we're asked to determine if the function has an inverse function, and in 2, give a reason for your answer based on the definition of the function and the graph that's given to us. Now, I've reproduced this graph here again because I might want to go back up here and look at it. Here's how I attack this. Well, the first thing I said is I answered part I here. I said, well, no, f doesn't have an inverse function. For my own benefit, why? Well, it fails the horizontal line test. Now, that's not sufficient for part 2, but I wrote it down in my way of thinking about this because I don't have an analytical expression for f. So how do I know that it doesn't have an inverse? Because when I draw a horizontal line, I can draw a horizontal line several places where there is more than one value of x that leads to the same value of y. In fact, we saw that up in part A. So there are at least at least two outputs that produce the same output. And for example, I know that f of minus 3 is equal to f of 0, which is equal to 1. And in fact, this is the sort of thing that they were really looking for in scoring this problem. They really wanted to see some specific values here, not just some sort of general appeal to the graph. So to back that up, I can go down here a little bit. Here are the scoring guidelines. 1 point for saying f does not have an inverse. So recognizing that, reporting that. And 1 point for the reason. Why? Well, there are output values of f that are mapped from unique input values. For example, we know from part A that f of minus 3 and f of 0 and f of 3 all return the same output value. So we have to appeal to specific values here. We can't just say there are output values that are not mapped from unique input values. We can't just say that. So Vicky, help me here a little bit on these scoring notes. I'll do my best. So the first point is earned for a correct answer. That is that F is not, or F does not have an inverse. If a student says F is not invertible, I believe they accepted that. That's okay. So both points may be earned in part 2 in some sense, provided there is no incorrect response. So I'm going to interpret this in the following way. A student could simply say something like this: no, F of 0 equals 1, F of 3 equals 1. It's sort of a minimalist response, and I believe they would earn both points.
So Steve, so it kind of goes back to calculus when we talk about we don't want a definition or just kind of a pat answer that covers
good
everything.
Point. Good point.
They really needed to pull some information from the graph that
Yep.
gave validity to why they were saying either doesn't pass the horizontal line test, is not invertible, these kinds of statements. They wanted some evidence that students were looking at the graph and understanding why it wasn't invertible or why it didn't pass the horizontal line test.
Yeah, excellent point. We don't want a definition.
Right.
We want you to use the information that's given in the problem, in this case, the graph, to answer the question.
Yeah.
And that's kind of, I think, supported by this bulleted item, this next bulleted item here, where it says they have to reference specific values.
Yeah.
So here's an example of a possible response. The graph of F is not invertible because not all input values have unique output values. Well, that's kind of a nice answer for one point, but it's not good enough for the second point.
Correct.
It doesn't reference specific values.
Yeah. So,
okay.
I mean, that's something that students need to practice, or teachers need to help students practice, is give evidence of what you're saying in other words, back it up in some way so that you make sure that you earn that full credit for that part of the problem.
So this next bulleted item gives it another example of how students could earn both points.
Yeah.
By again referring to specific values. F is 1 to 1, F is not 1 to 1, excuse me, or F fails the horizontal test. That's not sufficient to earn that second point. So even though I wrote down that in my solution, I had to go further here in order to earn that second point. Again, I wrote that down as thinking about, well, looking at the graph, why doesn't it have an inverse? And let's see, there's a couple of other little ones here I had down at the bottom, if I can get to them. The second point cannot be earned if there are any errors in 2, of course. So this is kind of an odd one, but I think some students actually did this. So they wrote something like, the function is not invertible because some inputs give the same output value. Okay, it's not invertible. They've earned the first point. They've actually appealed here to specific values of the function. And then they say it would be invertible if each input had a unique output. Well, that's not correct. That's kind of the definition of a function. A function for every input has a unique output. But that does not give a definition having an inverse function. So that last sentence is incorrect. It's kind of an example of saying too much. So that student would earn just the first point for saying that F does not have an inverse, or that F is not invertible. So this is kind of a second example down here. It says to have an inverse function, there must be no repeated x's and y's. And what I'm going to assume here in this response is that the student has already earned the first point. So let's suppose they say to me, okay, the function F does not have an inverse. So they've earned the first point. Now they say, well, to have an inverse function, there must be no repeated x's or y's. In the graph of F, there are repeated y's. That's close, but it doesn't give me specific values of x and y. And so that student would not earn that second point. Okay, in the bulleted one at the bottom here, there's kind of another one of these instances where a person can earn some partial credit, and we won't go through that one. Fantastic. Curtis, we got through one problem anyway.
Yeah,
Can I
I'm
take it?
wondering. Yeah, we did. We got through one problem anyway. Do you
Let me take a quick look at that calculator.
Sure, sure.
Okay.
So while you're popping that up, Steve, just a reminder to folks, a couple things. One, I have a professional development link that I'm going to put in the chat here in just a second. I might have already done it. I can't remember. No, I haven't hit enter. Now I'll hit enter. The second thing is that, and now people know how long the delay is, because if they're really good, they can count from when I hit enter and they saw it pop up to when I started talking about it. So the other thing is that what Steve is showing here is the ability to embed the TI-84 graphing calculator into a digital exam. As you may know, the AP Precalculus, along with every other AP STEM course, are going to go and become a hybrid version this next year. And as it stands now, they're going to use that the blue book that they use with the SAT. And it's not yet known what the graphing calculator available, the digital graphing calculator availability would be on that exam, but and you'll be able to bring your handhelds, your graphing calculator, the physical ones. But if you're looking for the possibility of a digital version of the TI graphing calculator embedded in that exam, College Board is looking for some feedback. There's ways to get in contact with them. You can even just post on the Twitter, or I guess it's called X now, or one of those other social media places, and tag them and give them a shout that this is interesting to you. But Steve, you can go ahead and demonstrate what
Sure.
this looks like and how it could work.
Yeah, this is, I think, very cool. So this is not actually Blue Book. This was developed by Texas Instruments to simply
Sure.
show that you can have a calculator embedded in an exam, in a multiple choice exam like this. So up in the top left-hand corner, there's a little icon for the calculator. So if I want to solve this, if I want to use my calculator to solve this problem, in this particular example, I can bring up any one of these four calculators, but I'm going to bring up the 84. There is also another version of this where you can bring up the TI-Nspire. The TI-84 is probably the most common machine used. So this will bring up sort of this picture of the 84, and I can use my mouse here to hit the buttons on the calculator. I really think this is kind of cool. So if I wanted to solve this problem, or attempt to, I might type in something like this and subtract off 1524 times this percentage, this decimal, which is 0.245. And there's my answer on the screen. I can pick it right out over here in my four possible choices, and I'm good to go.
Yep. And you can utilize the little arrow on the left-hand side of the bottom to resize it if you've got, or if you want to reposition the calculator somewhere, you can do that. Drag it around on the screen. For some reason, you need to pop it up someplace else. So there's a lot of nice little features of that. And then you can close it back down when you don't need it for other questions.
So, Curtis, what happens if I have this open and I go to question 3? Does it remain open?
It depends on how it's implemented by the exam provider. So that
Okay.
that then becomes something for the exam provider. It could reset the state.
Yes.
It could completely close down. It could maintain all of the information, but all of that is really controlled basically by the exam and how they want to run it.
So it is possible that if I go to question 3, let's suppose I close the calculator and I go to question 3 and I open it up again. It's quite possible that it's a brand new state and I've lost my information that was in there. It's quite possible it just starts anew.
It's possible that it could start new, but that's a definition by the exam.
Gotcha.
So it is also possible that it could maintain the memory and
Yep.
everything from question to question. It just depends on how they want that to go.
Gotcha.
I got a question from the chat. Lori asked if you could resize it for a bigger screen, and the answer is as big as you can make that little draggable unit there. You can make that screen bigger and bigger and bigger.
It's getting bigger. There we go.
There we go.
And play with it.
How about that?
Yeah. So
Yeah.
you don't want to
Depends
cut
on-
off too much of the question. So
Depends on whether you have young eyes or old eyes.
right.
Okay, very
So
good.
what we want everybody to know is that this is a possibility. And so let your voices be heard, that you would like to see TI technology on the digital exam.
I
Yes.
actually found this very easy to use, Curtis. I actually find
agree.
using the mouse almost easier than going to my handheld to get an answer. I kind of like seeing everything right here on the screen. I think there's less of a chance in my mind of making an error in taking the information from the question and putting it into the machine.
True, because it's right there beside the
It's
question.
right there. Yeah, it's right there beside the question. Yeah. Yep.
Nice.
Very good. Okay.
All right. Well, thank you guys very much. Yeah, this was a good session. Really enjoyed it. We will be joining or starting again here for pre-calculus in about a month on
Right.
September the 19th is our next session. So join us then. Otherwise, we will see you around. Thanks very much.
Thanks, everybody.
Thanks, Curtis.
Bye.
Bye-bye.
Bye.
All right. I think that's it.
Beautiful.
Good.